For this video, I will discuss how this alternative interpretation of physics could potentially work with the standard model of quantum mechanics. For the most part, this will involve simply interpreting results differently, as only a few things would need to change. As a disclaimer, I will not be trying to debunk or call into question the standard model, because quantum mechanics is already a very good description of reality that can accurately predict and model particle behavior. It's good science. Physicists are studying real phenomenon and trying their best to understand them. I felt the need to clarify this since it's commonly believed that local models are completely opposed to quantum mechanics, which largely comes from how most proponents of a local and real universe tend to argue their position by attacking the legitimacy of quantum mechanics. But that isn't really true with this interpretation, which takes a position closer to the one expressed by Einstein, that quantum mechanics is a good description of reality, but is nonetheless incomplete. What I believe makes it incomplete is mostly about perspectives on scale and our place within the universe. Under quantum mechanics, it's commonly assumed that the universe has a definitive small scale, most probably defined at the Planck length. This would imply that a smallest, most fundamental unit of reality exists from which everything else is built. Because whatever exists at the bottom of the universe can't, by definition, be made of anything else. It's at the floor of the universe. Nothing can be smaller. So everything else would have to be an emergent phenomenon of the smallest, most fundamental thing. And if there really is a floor to the universe, it implies that there are limits to the structure formation at the largest scale. So in the standard model, all matter and energy exist between a largest and smallest scale, and we just happen to exist very close to the center of all things. On the other hand, what I am proposing is that the universe may have an infinite scalar dimension, where stuff could potentially exist at infinitely larger and smaller sizes. The smallest particles and fields we can observe may not be the smallest things in existence. They're just a limit of what we can measure. So even what we call the fundamental particles could be emergent phenomenon of even smaller scale energy fluctuations. And we wouldn't be at the center of the universe. We would just be an insignificant speck without any true measure of where we are. Our position in reality only ever relative to what's around us. Which would mean that the measurements and laws from the current model of physics are true, but only for the scales that encompasses our observable universe, and only from our perspective. There would be no smallest thing in existence, only the smallest things that we can measure and observe. Quantum mechanics would still be good science, as researchers are taking measurements of real phenomenon and making accurate models of this observed behavior. It's just that these results would be interpreted under the wrong context. Under this interpretation, our observations are just the universe as we can see and measure it from our perspective at our scale using the tools we have access to. There wouldn't have to be many changes made to quantum mechanics for this kind of local and real model to work then. It's primarily about how quantum fields wouldn't really exist. They would just be a mathematical tool used to describe particle behavior from our perspective. There's a common belief that the smallest and most fundamental thing in the universe are particles. This is somewhat reinforced by the standard model being represented by this chart showing all the elementary particles that have so far been discovered along with their properties. But in quantum mechanics, there's something even more fundamental: quantum fields. The idea is that at the smallest scale of the universe, there exists a multitude of overlapping quantum fields which are the medium that create particles and through which interactions occur. There are at least 24 quantum fields, one corresponding to each particle in the standard model. This total may be higher, but at a minimum 24 fields are known to exist in the universe. Elementary particles are just an excitation within a quantum field. Larger particles like protons, neutrons, or even an entire atom do not have a corresponding quantum field. Their existence is emergent from the interactions of the fields of elementary particles. In this model, these fields exist everywhere, and they overlap each other at every point in the universe. Particles are excitations within these fields, and interactions between particles occurs through one or more quantum fields. When two electrons interact, they can create a photon. Under the standard model, what is actually happening is that an interaction between two excitations in the electron field generates enough energy to create an excitation in the photon field. The quantum fields themselves are basically just tensor fields, and tensors are a mathematical way to hold information about some property at some point in space. multiple tensors can be used to calculate changes in values between different points. A tensor field, then, is where every point in some region of space is assigned a tensor. This creates a grid of values that all represent some property, and can be used to demonstrate how these values change over time. For quantum fields, the information being tracked is the position, movement, and energy of different particles in a region of space. When a particle is said to exist somewhere, it just means that around some point in a tensor field, there are values that reflect that a particle could be there, which can be represented by these diagrams. This model gives a way to mathematically describe the position, movement, and interactions of different particles. However, it's far too complicated to handle every elementary particle within a single tensor field. Far too much information would have to be tracked, as each elementary particle has its own mass, charge, and spin. This greatly increases the amount of information that would need to be kept at every single point in space if everything were represented on a single field. This was overcome by each particle being described by its own field. All up quarks are described within a single quantum field, while all down quarks are described in their own separate field. The same is true for generation 2 and 3 quarks, all described by their own fields. Which is why there are at least 24 quantum fields. There's one for each elementary particle of the standard model. The values in a field will describe the position, energy, and momentum for a particle, and the field itself will describe the properties of mass, charge, and spin. This simplifies the math greatly, as the values for different fields can just be added together later. This is the mathematical model that makes it possible to describe and predict the behavior of a number of different particles all moving and interacting at the same time. It really is clever and works exceedingly well. But as I said before, under this interpretation, these quantum fields wouldn't actually exist. Or at least there's no reason for them to exist in a universe that has an infinite scale. They can only ever be real in a universe that has a definitive bottom size to it. Quantum field theory came about from the difficulty of early efforts to model particle behavior, as most physicists assumed that if particles had a real physical presence, then they must exist as inert spherical objects, something like tiny marbles that travel through the fabric of space. Because it's believed that it's impossible for there to be any internal movement within an elementary particle, a consequence of assuming a finite scale to the universe. And models of marble-like particles don't work. It's impossible to describe the behavior of particles this way. However, it was eventually found that a particle's behavior could be approximately described as tiny spheres traveling on a bed of springs. While it wasn't believed that the universe was made of infinitely many tiny springs, the oscillations this created for the particle could describe their behavior reasonably well. It captured the wave-like behavior seen in particles while keeping the particle an inert sphere. This work was then built upon and turned into the field equations of quantum mechanics. Tensor fields are used instead of springs, which can model the wave-like properties observed in quantum objects. But if quantum fields are real, then particles couldn't be inert spheres anymore. Instead, they would have to be an emergent phenomenon of these fields. So particles began to be seen as just vibrations within the fields. And this does work incredibly well. There's no denying that. However, if we instead assume that the universe has an infinite scalar dimension, then all of this can be interpreted very differently. To start, the difficulty in describing particle behavior before quantum field theory would have been because particles were seen as inert spherical objects, instead of the dynamic fluctuating systems that they could possibly be. In this case, the behavior of particles would come from their internal motion and the interactions between the objects they are made of. These kinds of particles should be able to drive their own motion. And since they have spin and angular momentum, they should have rotational motion, meaning that we should expect wave-like behavior from local and real particles, because they are dynamic systems of fluctuating spacetime with rotational motion. Which means that instead of the wave in the quantum field driving the particle is driving the wave, and smaller scale interactions and systems of objects are driving the particle. This would also mean that quantum field theory would be an inverse model for this kind of real particle, where, in order to model a particle's behavior, the area around it is modeled in place of the particle itself. Quantum field theory would then be a mathematical model of the motion of space around a particle, where the properties of each particle are just tacked on later, where the equations say where a particle might be, and when it's found, it will just have these properties. This does work for our observations at our scale, I mean, it retains all relevant information about each particle as if it were still real and present. And particles do fluctuate and travel as waves. But if there's an infinite scalar dimension, then particles could have a real structure that can drive the behaviors that we observe. And so under this interpretation, quantum fields could then only be a mathematical tool for describing particle behavior by modeling the fluctuations around each particle. It would still be good science. It's a clever way to accurately model the movement and interactions of particles from our perspective given the limitations of our ability to observe the universe. But this does not mean that the fields themselves physically exist. Because if the universe does have an infinite scalar dimension, then what would it mean to be a smaller size than a quantum field? If you could shrink down in scale so that the Planck length was the size of what planets are to us now, then what would you see? What would it mean to look around at the sky and see some 24 overlapping fields that can each generate particles when they get excited? There aren't any good answers to such questions because quantum fields were designed under a framework where there is a definitive bottom floor to the universe. They are designed to describe what we see of particles from our scale. By design, they can't answer what they look like at any other scale. And so, if the universe has an infinite scale, then quantum fields don't really exist. This does raise an interesting problem, though. Spacetime and quantum fields both originate from descriptions of field equations, which means that I'm saying that one set of equations describes a physically real entity, but another set is just an abstraction of reality. This may seem like I am picking and choosing what to believe, which is likely. However, there's already a precedent for doing this exact thing, as some quantum physicists think that spacetime doesn't exist, but quantum fields are in fact real. The claim would be that gravity is not caused by the warping of spacetime, as described by general relativity, but rather by quantum fields associated with a graviton particle. This comes from two things. First, that general relativity does not currently work with quantum mechanics, so at least one of them must be missing some kind of information, or may even be wrong in some way. And there's also the assumption that the scale of the universe is finite, and therefore a smallest size exists. Because of this, it is often believed that quantum mechanics is the study of the smallest and most fundamental things in existence. This has led some researchers into taking the stance that space and time aren't real, as it's not described by the equations of quantum mechanics. Instead, spacetime would just be an emergent phenomenon from the interactions between quantum fields. Not that this is a universal belief amongst scientists, it's just that this is a serious position that some physicists hold, which is consistent with the standard model of quantum mechanics. It at the very least shows that relegating a field equation to nothing more than a mathematical model, and not a real entity, can be a serious possibility. This interpretation just takes that in the other direction to say that quantum fields are just a model, and spacetime is actually real. Not that general relativity is fundamental to the whole universe, but that under the framework I am proposing, our experience of the universe is relative to our scale. And we are able to most accurately measure and study the scales nearest to us. We can measure and study spacetime around us. We can see it warp, wave, and distort. And we can see objects in the universe interacting with it. But quantum fields lie at the extreme edge of our ability to observe the universe, and only exist as math equations used to describe particle behavior. I would just argue that spacetime not only has more evidence to support it being real, but that it has more explanatory power for the overall properties of the universe. The behavior of particles is best described as waves, but they're always measured as particles. This is wave-particle duality, and it's commonly seen as a problem in physics. The consensus opinion is that particles exist as waves until they are measured in some way, at which point the wave function collapses, and they behave as a particle. Under the alternative interpretation of this series, a particle would be a dynamic system of interacting structures made of spacetime all nested across a multitude of scales. It has what can be considered a real location that it exists within, and real properties at all times. Most movement in the universe is rotational, for a few reasons, like how massive bodies move and interact in a three-dimensional space. This would mean that particles always exist as particles, but that they travel and behave as fluctuating waves due to the rotational motion of their entire structure and internal parts. Which may have some experimental support, because particles are only ever measured as discrete objects. For example, it's possible to track the movement of particle debris after a collision event inside a particle accelerator, and this will always result in trajectories of discrete objects, not waves. The usual response is that we see individual particles here because they're being measured, so of course they appear to be discrete objects, which is the strange state of particle physics. Whenever we have a real measurement of a particle, it's as a discrete object at a single location. Before that measurement, the math and the theory claims that it's a probability wave. So of course the consensus opinion is that the math is the reality. But if we just consider the possibility of an infinite scalar dimension, then there's no wave-particle problem. Particles could just be real objects. They would have some rotational energy whose movement would best be described by a wave function. Especially if more time is experienced by quantum objects relative to us, as what we would see of a particle's motion would be some larger amount of time for them relative to us. So local and real particles would be discrete packets of energy that travel in a wave-like manner under their own internal motion. While quantum tends to refer to small-scale things, it doesn't actually mean small. Instead, it refers to quantity. The reason that the small scale is described as quantum is because elementary particles come in discrete packets of energy, or quanta. A photon can have some quantity of energy within it. If we define some value for the smallest amount of energy a photon can have, then all other photons can either have this value or some integer multiple of it. They will never have a non-integer multiple of energy. It will always be some discrete quantity. This quantization is an important feature of quantum mechanics and helps separate it from the physics of the large scale. At the scale that we reside in and above, it's possible to have any non-integer value variation in mass and energy. Most things just don't come in discrete packets. However, there's a possible explanation for this property under the framework I am proposing. First, we do see quantization in large-scale objects, although it's mostly from things that are undergoing tension, like a cable or thread that is attached to something. Think of the strings of a guitar. When they are plucked, their movement is restricted such that their movement will always be in some discrete value, or quanta. We just call these chords. The movement of guitar strings is therefore quantized. If we run with this idea a little, the local and real particles I have proposed are dynamic systems of interacting spacetime, which are attached to the rest of the universe at every point over their surface area. This would mean that each particle is connected to, and in tension with, the rest of spacetime. And if spacetime has real properties, then there would be limits to the amount of movement or distortions possible within any region of the universe, which is indicated by such things as the speed of light and gravity. Or more directly, the Planck constant, which defines the relationship between a photon's frequency to its energy. If everything is just fluctuations in spacetime, as I am arguing is possible, then this value would define the energy contained in fluctuations of spacetime at that scale. So the strength and force of the tension with spacetime warping should have clearly defined values based on a particle's mass and energy. This could explain why certain mass energies are more stable than others. It's as a result of how much movement is possible in any region due to the properties of space. And thinking of this over an infinite scalar dimension, it would be more stable masses or energies at smaller scales that persist long enough to build into larger structures. And where it's the more stable structures that can hold together and interact to build into even larger scale structures. Or at least that's a start to a possible physical explanation for the quantization of particles. What I've been discussing so far has been mostly relevant to the particles that make up matter, what are called fermions. These would be the quarks and electrons, as well as all of the particles of matter they create. But there are also the bosons, which are the force-carrying particles in the Standard Model. Bosons don't interact to form matter. Instead, they mediate interactions between the fundamental forces of the universe. These forces include the electromagnetic force, the weak force, which is involved in particle decay and other interactions, and the strong force, which is the binding interactions that keep particles together as a single unit against the repelling forces trying to push them apart. There's also gravity, but that is currently best described by general relativity, where it's created from the curvature of spacetime. In the Standard Model, all the forces, except gravity, are united by the fact that they are described through the interaction of boson particles. Or rather, by the excitations in boson fields. The electromagnetic force is mediated by the photon, the weak force by the W and Z boson, and the strong force by the gluons. In the interpretation I am proposing, these bosons would either be fluctuations within spacetime, or they would just be more particles, which would be dynamic interacting systems of spacetime. The bosons would still exist, but not as they are under the Standard Model. Under this interpretation, the electromagnetic force would be the flow of spacetime created from the movement and interactions of physical matter. There would be two main sources of motion within the particle that could possibly create some force or interaction: the rotation and movement of the particle itself, and the motion and interactions of the smaller scale things they are made of. So how would this create electric and magnetic fields? I don't want to speculate too much about new physics or new phenomena, so I'll try to keep things within what is known. So I'll just stick to referencing stars and planets. Magnetic fields are represented by a flow of energy through an object. So far in nature, we have only found dipole magnets, where there are two ends to the field, one negative and one positive, as opposed to a monopole that radiates either a negative or positive field, which has never been encountered before in nature. So let's take it for granted that this flow is what makes a magnet a magnet. It means we need to find a current that runs through a structure. Well, in stars and planets, their magnetic field is made from the movement of molecules and atoms within their mass. In planets like the Earth, it looks like it comes from the flow of matter in the planet's core that generates the magnetic field. There's still some debate about where a star's magnetic field comes from, but it appears that it may come from the flow of atoms through different layers of the star. Either way, it's basically the movement from the molecules that make up the superstructure that generate the field. Stars and planets don't have a charge, but they do have rotational motion as they spin and rotate. This motion also warps the spacetime surrounding them in what is called frame dragging. So to start, the magnetic force has a pretty straightforward explanation in this interpretation. If elementary particles are made up of some number of smaller scale objects, and these objects also have a charge, then the movement of these objects within the particle could potentially generate a magnetic field, which would mean that charge would have to be a property of the rotational motion of a particle. As they travel, they rotate and spin, which causes distortions in the surrounding spacetime. Sort of like gravitomagnetism, but not exactly. So the electric and magnetic force would possibly be types of directional spacetime fluctuations caused by the movement and interactions of regular matter. Which is also kind of like dark matter in this interpretation, where the motion and interactions of different cosmological objects creates movement and fluctuations in the surrounding spacetime. This creates a real and physical effect that radiates outward well beyond the regular matter. The elementary particles and the things they are made of should also be able to warp and distort spacetime in much the same way. And these fluctuations would have a real physical presence in the universe. Except that the fluctuations created in the particles would be experiencing more time than us, which should make their effects greater than how they would appear at the scale of the particle, as we would be seeing the particle over some longer stretch of time, causing us to see more pulses or fluctuations in these fields. At least that's the best I can come up with for a local and real interpretation of the electromagnetic force. It could come from the movement and fluctuations from the elementary particles and the things they are made of over an extended amount of relative time, which means that under this framework, the electromagnetic force is mediated by the movement of spacetime and not photons. But as I said in the fourth video, it could be possible for photons to be objects with mass, that it's only from our scalar perspective that they appear to be massless. Photons would then only be related to the electromagnetic fields because we can only detect the fluctuations in spacetime they create. The weak force is involved in a variety of different particle interactions. It's most often discussed in terms of its role in neutron decay, so I will use that for my example as well. Neutron decay typically happens to neutrons in an unstable environment, meaning free neutrons not part of an atomic nuclei, or ones that are a part of an unstable isotope, which are atoms with too many or too few neutrons. To become more stable in this case means becoming a proton. Neutrons are made of 1 up and 2 down quarks, while a proton is made of 2 up and 1 down quark. In neutron decay, a down quark turns into an up quark, which involves the quark losing mass and a full -1 charge. The extra energy that is lost in this interaction is called the W boson, and is one of the particles that can mediate the weak force in the Standard Model. This particle does not exist for long and decays quickly into other particles, in this case, an electron and an electron antineutrino. In the Standard Model, the down quark doesn't just transform into an up quark. Instead, it interacts with the up quark field and creates an up particle. This interaction creates enough energy to interact with the W boson field, which creates a W boson particle. The W boson then quickly decays, interacting with the electron antineutrino and electron field to produce their particles. The possible explanation for this interpretation is just a little different. When a neutron is in an unstable state due to its surrounding environment, the neutron is eventually forced to reach a stable state. This causes a down quark to lose mass and energy. The combined energy lost from the quark is still an energy packet that could be called the W boson. Under this model, quarks should be made of smaller scale objects and the interactions between them. And so the mass and energy that the down quark loses would need to be some combination of interaction energy and small scale object. This energy is ejected from the down quark, making it an up quark, and the energy becomes an electron and an electron antineutrino. This could be because the mass of energy contains a set of constituent parts that can interact to form an electron and a neutrino. So the W boson is an intermediate step between this energy being ejected and those parts forming into other particles. But there's also the possibility that the whole electron was ejected from the down quark. That electrons are just a constituent part of down quarks, because electrons seem to be an exchange unit in quarks. There's also a thing called electron capture, where an electron will be drawn into an up quark of a proton, turning it into a down quark, and changing the particle into a neutron. So perhaps entire electrons are a constituent part of down quarks. If not, then the component parts of an electron are also component parts of quarks. In either case, under this interpretation, the W boson in neutron decay is just a description of the particles and energy ejected from a down quark. It's not an excitation in a quantum field. The strong force binds two or more particles together, even if they would otherwise normally repel each other. Two protons, for example, will repel each other if they get close enough because they have the same charge. However, inside the nucleus of an atom, there can be a number of protons in close proximity to one another. They don't repel each other, instead they can stay together as a single unit. The protons are being held together by the strong force. The strong force also keeps quarks together in protons and neutrons. But I'll start with the strong force between protons and neutrons in the nucleus of an atom. The Standard Model explanation here is that the quarks between a proton and neutron send virtual particles back and forth between each other. This interaction creates a bond that keeps them together. The reason virtual particles are used is because they can mathematically represent an amount of energy being transferred between 2 points without the quarks needing to expend or gain all that much energy during the process. In other words, it works mathematically. So here's a possible explanation under this interpretation. To create atoms larger than hydrogen and helium usually requires some high-energy environment, such as from the heat and pressure of the interior of a star, or when a star goes supernova. It takes this extra amount of energy to get multiple protons and neutrons to overcome their natural repelling force to come together in a nucleus. The idea then is that protons and neutrons don't have a smooth and evenly distributed electromagnetic field surrounding them. If they were physically real, these fields should come in shells of different strength. So the act of 2 or more protons and neutrons bonding in an atomic nucleus involves overcoming the outer layers of each field. When brought close together, they could then begin to be affected by the inner shells of these fields. At the innermost layer, they'd originate from the quarks. A proton is made up of 2 up and 1 down quarks. This means that while a proton has an overall positive charge, at very close range, they are made of 2 localized positive charges and 1 negative charge. Neutrons are made from 1 up and 2 down quarks, so even though they have an overall neutral charge, neutrons are made of 2 local negative charges and 1 positive charge. So when protons and neutrons are pushed together, they should stop interacting with the charges of their outer shells and instead interact with the innermost shells as well as the individual fields of the individual quarks. This allows for new bonds and interactions to form between these inner shells, thus binding them together into a single unit, a nucleus. Once bound together, they now create a new field around them based on these interactions. This means that we should expect that atoms with multiple protons and neutrons should bind together into three-dimensional structures, where the overall shape and design is based on the local interactions between particles and particle groups. Like the recent experiment that was able to prove that the nucleus of a beryllium-10 atom has a dumbbell shape. This interpretation would predict that all atomic nuclei are in some three-dimensional structure or shape built from local interactions between particles. But the shape of the beryllium-10 nucleus was actually predicted using the Standard Model many decades ago. This paper is just a confirmation of established theory. Except that, for the Standard Model, only some atoms have this clearly defined structure. Under the alternative interpretation of this series, all nuclei would have clearly defined three-dimensional structures, although the state and shape of those structures may change over time. And this is because we should also expect that the protons and neutrons to still be moving and fluctuating inside of this nucleus, as they would still possess rotational energy. So these structures should shift and fluctuate with time. The degree of these fluctuations would be determined by the design of the structure, and the properties of the overall atom would in part be based around what structures form for each atomic number of protons and neutrons, and how they internally fluctuate. This framework then gives a possible explanation for atomic decay, because this would mean that some number combinations of protons and neutrons are able to build three-dimensional structures where its internal movement and fluctuations are stable, in that the positive and negative charges even out over the entire region of the particle's nucleus, as well as over time. But some configurations would be unstable, where there are missing pairs of charges or where unbalanced regions of positive and negative charges exist. When a particle is in such a state, it could try to correct itself. This could either be by taking on another arrangement, or by ejecting enough particles to allow for a stable structure to be maintained. The degree of this imbalance should vary, where some combinations of particles create such unstable structures that they decay almost immediately into a different element or isotope, while other combinations are able to convert into a more stable structure for some amount of time. How often it goes back to the unstable configuration would dictate the decay rate of that isotope. At least that's a possibility for the strong force at the atomic scale. But the strong force that occurs between individual quarks is a bit different. In the Standard Model, quarks are bound together by gluons that pass back and forth between each quark. There's an entire theory around how this process works called quantum chromodynamics, but it's not necessary to cover it in great length here. Basically, there are different kinds of gluons, and how they get passed around between quarks affects the moment-to-moment structure and properties of that quark. A gluon will hold some property, and when it interacts with a particle, it changes the properties of that quark. The quark will then send out a gluon that corresponds with its current property to another quark, and then the process repeats. In this way, not only do gluons hold quarks together, but they also affect the properties they contain. Or at least that's the very cursory overview. Once again, under the local interpretation of this series, the strong force between quarks would have to be the interactions and motion caused by the quarks themselves and their constituent parts. And so each quark would be a fluctuating system of dynamic spacetime made of other such systems, and each quark in a particle would be moving around and interacting with other quarks in the group. They would then be bound by the spacetime distortions they create. The interactions that they form between each other then creates extra energy, detected as mass at our scale. This would be much like dark matter, implying that these interactions are influencing the velocity or movement of each quark, that more energy is being created from the interactions and distortions inside the particle, which could also be because quarks might be experiencing more time relative to us, meaning what we see of them is the average of some length of relative time in their scale. The gluons, the bosons of this interactions between quarks, would be the distortions in spacetime created from the movement and interactions of the quarks themselves. At least that's the most plausible explanation I could find. Under this interpretation, gravity is the curvature of spacetime, just as it's described in general relativity. This interpretation just adds that not only is spacetime real, but that everything is made of it as well. This may help to explain why the gravitational interaction is so much weaker than the other forces. Gravity is caused by the mass of an object, the amount of energy it contains. A massive object warps spacetime, which causes a gravitational interaction to anything nearby the spacetime that it is warping and curving. Under this interpretation, mass would be the total amount of energy that exists in the structure from the combination of all the objects it's made from and the interactions between them. Which means that there should be more spacetime in a region that contains mass compared to one that is empty, in order to make the objects and interactions within it. This extra spacetime must come from somewhere, which would be from the structure and its component objects pulling in spacetime towards themselves. This should create curvature of space around a structure with mass. And because it's happening in 3 dimensions, it's a geometric increase in the amount of spacetime being pulled towards the structure the further out we look. So the warping of spacetime diminishes in strength exponentially from its source, which could be why gravity is the weakest fundamental force. As for how particles that are made from spacetime are able to move through spacetime, they would thread themselves through the universe. A particle that is in one location will be pulling in spacetime all around itself. But as the particle moves in one direction, it will begin to pull more of the region in front of it. At the same time, as it leaves that location, it will release some pull on that region behind it. And this keeps repeating each step on its trajectory, where what regions of the universe are affected by this interaction changes with location. And in this interpretation, every particle is made from smaller components, which are each pulling on spacetime. So this isn't one pulling force. It's a layered action happening across a multitude of scales and over different lengths of time. With everything being made of the movement of spacetime, this means that things in the universe move by threading themselves through spacetime. And so mass under this interpretation is just how much spacetime is warped and distorted to maintain a structure and its interactions. Unlike the standard model that says that mass comes from the Higgs mechanism. The Higgs field is the explanation for why some particles have mass in the standard model of quantum mechanics. And under my interpretation, it doesn't exist. The Higgs boson is still most likely real, but it would be much less than the standard model would suggest. Of course, under this interpretation, none of the quantum fields really physically exist either. They're unnecessary as an explanation if the universe has an infinite scale. The Higgs field just isn't needed. Mass from particles would come from the warping and distorting of spacetime. But more than that, I don't think that the case for the Higgs field is very strong. Let me explain. There was a problem with quantum physics where it predicted that elementary particles wouldn't have mass, except that they did have mass. The only units that the theory had to work with were quantum fields and the excitations within them, and neither could explain why particles have mass. But during the 1960s, a few researchers independently came up with a solution to this problem through the addition of another quantum field. In this theory, the mass of particles would come from their interactions with this new field, such that the more a particle interacts, the more mass it has. And particles like photons and gluons that don't interact with the field at all will therefore have no mass. How this works is that unlike every other quantum field, the Higgs field has a constant energy potential. This can be diagrammed into what is called a Mexican hat potential, as it supposedly looks like a sombrero. These energy potentials exist everywhere at every point in spacetime and are what particles interact with to get mass. This explanation solved the issue mathematically, but would still need evidence to be proved. Except it's not actually possible to directly observe quantum fields, so it would probably always be impossible to measure this Mexican hat potential. But if this field did exist, then it should have a corresponding particle associated with it. This would be the famed Higgs boson. It should be noted that the Higgs boson isn't really involved in giving particles their mass. According to the model, mass is about particles interacting with the Higgs field directly. But if this field did exist, then this particle should too. So this is where the search for proof turned. However, it's also impossible to measure the Higgs boson directly because it should decay far too quickly. So instead, researchers went looking for the particles that a Higgs boson would decay into were it to actually exist. Or rather, they went looking for energy signals that corresponded to decay pathways predicted by a Higgs boson. This search was done through the use of particle accelerators, Large machines that bring two particles up to some extreme velocity before colliding them together inside of a detection chamber, where the resultant debris is analyzed. A Higgs boson, like many of the particles found in a particle accelerator, only occur in such high-energy events. In 2012, a signal that corresponded to the Higgs boson was found to a high statistical significance. And this signal is very much real. So if it's called a Higgs boson, then the Higgs boson is real and was officially discovered in 2012. However, I have some doubts that this proves that the Higgs field exists or that this is where mass comes from. I don't think that this signal proves that the universe is covered in Mexican hat potentials. Instead, I think the researchers found a high-energy event that can, on occasions, create an extra amount of energy which has a distinct decay pathway. But this doesn't prove that the Higgs field is real. Just that in this interaction, there's a small chance that more energy will be present, and this will decay into these products. The Higgs boson is just an amount of energy between steps in this process, where there was more energy than expected some of the time, just a fraction of a percent of all the collisions that occurred. The thing is, other signals of extra unexplained energy have been observed inside of particle accelerators. Many of these anomalies can be recreated, but just not to a high enough statistical significance to be verifiable by the standards of particle physics. Because of this, they're not considered to be real particles. And yet the detection of some of these can reach a significance close to the results for the Higgs boson before the Large Hadron Collider discovery. This in no way confirms the existence of these anomalies. The Higgs boson hit a level of significance that these other anomalies haven't, and that is absolutely meaningful and is direct evidence of its existence. However, the context for how these values were reached is also important. The fact that the Higgs signal had a decades-long worldwide search that included upgrading facilities or building entirely new ones, all just to improve the statistical significance during detection, is also meaningful. Because the search for these other anomalous signals hasn't received the same level of effort that the Higgs boson did. While there are a lot of physicists open to these anomalies being real, there is no consensus on what they could actually be. And outside of a few possible candidates for dark matter, the explanations being put forward generally don't work with each other, as there really isn't a good reason for them to exist in the standard model, as they would just be a packet of energy created during particle collisions that decay into smaller particles. They would just be like the other gauge bosons. But that's all that was detected of the Higgs signal. It's just an extra amount of energy created in a particle collision some of the time. It would take some explanation as to why the Higgs boson signal means a quantum field exists with a positive energy potential that exists everywhere, but these other very similar signals do not. However, that's what I would argue the Higgs boson actually is. A bit of extra energy that appeared every once in a while during this one interaction that resulted in more decay particles being present. It was actually impressive that the standard model was able to predict that this extra energy was even possible, as researchers were able to take a hypothetical packet of energy and ask their model where it might appear and what it might look like. But this is not uncontestable evidence for the Higgs field, only the strength of quantum mechanics. And ultimately, the Higgs field was created as an explanation for mass, which is only a problem because the standard model assumes the universe has a finite scale and the fundamental units of existence are quantum fields. However, if the universe has an infinite scale, then mass would just be something like the amount of movement and interaction in a region of spacetime at some scale over some interval of time. It would just very directly be about the warping of spacetime. There are a few things that I've yet to discuss that didn't fit in anywhere else. Quarks and electrons come in 3 different generations. Generation 1 are the most stable, and are what forms all the ordinary matter around us. Generation 2 and 3 have the same charge and spin, but have more mass than their Generation 1 counterparts. They're also not as stable, meaning they decay quickly into other particles. They're usually only created from high-energy events like collisions within particle accelerators. Without a more substantial model, I can't say for sure why this stability exists. It could relate to spacetime having physical properties, and as such, certain masses at certain scales are just more stable. Or maybe the substructures that they are made out of are unstable, like some isotopes. And I haven't talked about neutrinos because I honestly don't have much to say outside of what's already known. Neutrinos are particles created from certain high-energy events, or things like particle decay. They're also very unstable and decay quickly. What's really strange about them is that a neutrino can change which generation of particle it is while it travels, and it can do this multiple times, alternating between generations before it completely decays. Under this interpretation, because they have mass, they should have some structure. Changing generations would then represent changes to the internal structure of the neutrino. Each state is unstable and fluctuates randomly. But they are just stable enough for the neutrino to switch between these generations. But they have different mass from each other. This change could come about from alterations in the bonding strength between different internal objects of the neutrino, as with dark matter. The neutrino then fluctuates between these unstable states until it finally decays entirely, or something to that effect. And beyond that, neutrinos make for good models for time dilation. One source for neutrinos comes from the cosmic rays impacting the Earth's atmosphere. This creates neutrinos that then travel down towards the Earth's surface. But because they decay so quickly, none of them should exist long enough to impact the ground. Except that these neutrinos actually can and do impact the Earth. And this is because these neutrinos are traveling so close to the speed of light that they experience time dilation. This interpretation would add that these neutrinos, as well as all the objects they are made from, would be experiencing more time relative to us due to differences in scale. But this extra amount of time is stretched out from our perspective, as the neutrinos are experiencing time dilation relative to us, due to both its scale and velocity. Before I end this video, I'd like to mention just one more thing. One of the common criticisms against local models of the universe is that electrons couldn't orbit around an atom. It's simply impossible. This is because it takes energy for one object to orbit around another, and since the electron would need to spin around the atomic nucleus at an incredibly high velocity, it would require an immense amount of energy, which would mean that the electrons would lose energy over time and hence velocity, and would eventually collide with the atomic nucleus. But this is based on a local model where particles are assumed to be tiny marble-like objects sitting on top of or within space-time, and this doesn't work. However, there is the option that they are instead dynamic moving systems made of even smaller interacting dynamic moving systems. It appears that when an electron orbits an atom's nucleus, it's doing so because it's attracted to and interacting with the electromagnetic field of the nucleus. So if particles are local and real, then the electron is made of smaller scale objects. It's from the motion and interaction of these objects that the electron gets its properties. The sum total of movement and interaction inside the electron, and the electron as a whole, produces an electromagnetic field. When an electron orbits an atom, it does so through its electromagnetic field, interacting with the electromagnetic field of the nucleus. These electromagnetic fields are being produced by the particles regardless of this interaction. So it shouldn't be necessary for more energy to be produced for an electron to orbit a nucleus. The orbit of an electron around an atom, then, would be different from how a planet orbits around a star. I hope it was made clear before, but I am not trying to argue that quantum mechanics is bad or untrustworthy. Physicists have worked hard to accurately observe and model the properties of particles, and it's good, rigorous science. All I am trying to do is describe a possible alternative interpretation that isn't ever really considered. Because while the idea I have been describing lacks any proof or evidence, it is at least, in concept, compatible with almost all results and evidence that have been produced in the field so far. The biggest claim that I have made in this series is that quantum fields, including the Higgs field, probably don't exist. And even this claim doesn't require denying the evidence, just questioning the interpretation of some results, which mostly comes down to whether or not the universe can have an infinite scale. This does not in any way corroborate or prove my idea. Again, that would need more direct evidence and a working model. All that I am saying is that it may be worthwhile to at least consider the possibility that the universe may be local and real, where there is an infinite scalar dimension. If for no other reason than to push at the edges of the standard model, to perhaps look at it in new ways. There's one more video segment left. A conclusions section where I will restate my position and offer a few thoughts that didn't make it into the rest of the series. I hope you will continue to watch.